on this slide, you can see different density distributions of the same data. So we have the same number of values, the same data, but we use different number of bins. First of all, you can see that the scale of on all plots is the same. So the highest value on y, it's 0.1. Then you can see that the average height of all bars will be the same. But by using more bins, you sort of give more details what's going on inside the interval. And for example, the last case, this one, I think the number of bins is too large because your histogram is a bit noisy, so it gets like up and down, up and down, up and down. And then for the third case, it looks very good. It looks smooth, and you can see still some details. While the first case, for example, the number of bins is too small, so you don't see any details. And then I think that the second case, where the number of bins is 5, is also relatively small. Okay. What shapes actually you may see when you analyze data using distribution histograms? You remember that, first of all, distribution histograms are good for big samples, right? If you have like number of values is 100 or more. So you can see some interesting patterns. For example, in this case, on this slide, you can see a symmetric distribution here. What is symmetric? It means that if you make these tails, they look like they flipped or mirrored. So the shape is the same. The shape is the same, almost the same. This distribution is called uniform. It's a very interesting distribution because in this case, every bin has the same number of values. Okay, so it's uniformly distributed. The values are uniformly distributed. Sometimes it's called even distribution, so evenly distributed in all interval. In the last two cases, you have skewed distribution. What is skewed? Well, again, if you compare the tails, this one is pretty short, but this tail is long. You can see that the small bars here. Why? Because we have some extremely comparing to the other values, extremely small values here. So, and it makes it like, sometimes it's called heavy tail. Okay. In this case, we have similar situation, but now we have extremely large values. So this is the heavy tail, and then it makes this tail of the histogram longer, much longer than the left one. Okay. We will discuss some of these shapes and also how to calculate statistics that tells you how symmetric a distribution is and so on in the next lecture. If you compare the density distribution with cumulative frequencies, then in this case, you remember that cumulative frequency, for example, if we take this point, it tells you how many values in percent you have below given. Okay, so in this case, you have, let's say it's 71, and then that's the cumulative frequency for 71. So it means that about 80%, in this case it's 79.3% values are below 71. Okay, so the point on this curve corresponds to the area on this distribution. This is density distribution. So if you see this 71 is here, and how many values we have below 71? Well, it's a total area of all these bars on the left. So summing up, density distribution, height of each bar is a density. It's number of relative frequency of the values divided to the width of the bar. So it means that area of each bar is the relative frequency. And in the shown plot, the red area, it's a percent of the values equal or below given in this case. Okay. And then if you look at the cumulative frequencies, point in this curve is a percent of the values equal or below given. So it means that the point on the cumulative frequency corresponds to the area in the density distribution and vice versa. And just to remind you that cumulative frequencies are always positive, never go above 1, because 1 corresponds to 100% of the values, and it never decreases. It either remains the same or growing. Well, that was the last slide in this lecture. Let's sum up what statistics and what plots we have learned to describe interval of random values. Well, first of all, we know that we can describe the spread of the values using mean, max, and range. So it's the smallest, the largest value, and the difference between them. We can use median to find a center of the values, where the center of the interval is. Then we can use quantiles, quartiles, percentiles, frequencies, and densities to describe what's going on inside the interval, in different parts of the interval, where we have more values, where we have less values, where the interval is more dense, where the interval is more sparse, and so on. So the behavior of the values can be described using these statistics. And then, of course, plots. Plots are extremely important because you can't get a feeling about your data without looking at it. And plots allow you to look at your data from different points of view. And the first is a dot plot. If you have a relatively small sample, that's one of the simplest and still efficient plots. So you will see how the values are distributed. If you have more values than one of the other plots, you can use as box and whiskers plots based on quartiles. It gives you a quick and dirty overview of what's going on with your data. Do you have symmetric distribution or not? Do you have any heavy tails and so on? And then, of course, you can use distribution histogram, frequency, relative frequency, or density distribution, and the cumulative distribution curve, also to see what's going on with your data and what's going on in different parts of your data.